Let's open MATLAB and start to learn how to code the gradient descent algorithm. By clicking on the new script icon on the left, we can open a new script file and we can save it as gradientmethod.m. We need the function plotRobotArm to plot the robot arm configuration. So we need to tell MATLAB where it is by using the command addPath, specifying the path to the folder where the function is stored. Now, to translate our pseudocode in MATLAB, we start by defining our input parameters. So the target point xp with its two components, the arm's length L1 and L2, the initial guess for the angles in radians, the tolerance for stopping the algorithm called toll, the learning rate alpha, and the maximum number of iterations. So since convergence is not a priori guaranteed, we fix this maximum number of iterations to 1000. And this will prevent the algorithm from running endlessly. We also need to be able to compute the tip position given the angle as in this formula. So to this end, we define the new function robotPosition, which takes the angles as input and returns the position in the xy plane. We can print the coordinates of the robot tip giving the initial angles as input, and using the function we just imported, we can visualize the corresponding robot position. Moving on, we now look at the iteration loop. Notice that at each iteration, we will need an evaluation of the function j and of its gradient. So to this end, let's implement two functions. For the function j, we use the following syntax. First, using the function robotPosition, we compute the position xy, and then we can compute the square distance j simply using Pythagoras' theorem. And if we want to test this function, we can print the value of j for the initial value of the angles, and of course, this value is very high. Next, we define a MATLAB function called gradj, which takes as input the angles θ1 and θ2 and outputs the two components of the gradient. So given x and y as before, we now need to compute the partial derivatives. For instance, the derivative of x with respect to θ1 is coded in this way, and similarly all the other terms. So finally, we use all these terms together to write the two components of the gradient of j. Now we have all the ingredients to code the iteration loop. In particular, we implement a while loop. So we set the iteration counter I to 1, and while I is smaller than the maximum number of iterations, we perform these instructions. We compute the gradient using the current angles, the target point, and the corresponding function. Then we update the angles, and then we compute the cost function j to check the stopping criterion. And if the stopping criterion is satisfied, we can print the number of iterations reached at this point, and the instruction break interrupts the loop. Otherwise, we simply increment the counter I and move on to the next iteration. To check the output of our algorithm, we can print the final angles combination, the computed square distance, and the final arms configuration. So let's run the script, and let's have a look at the results. So the method converges in 38 iterations, and the numerical solution is this pair of angles, 0.62, 4.68. And the final square distance j is between the tip and the target is about 0.008, which is in fact smaller than the tolerance we chose. So the method works. We found a pair of angles to reach the target point. And remember, these angles are in radians, so in degrees they correspond to more or less 36 and 270 degrees. Now, a question for you. What do you think happens if we change the starting point?